Okay, so let's begin. Uh, Namaste. So today is lecture 2 of Thermodynamics of NPTEL course ME78. I am Priyanka Rajeev from Department of Mechanical Engineering, IIT Kanpur. Today we will be seeing week 2 lecture revision and revision questions from week 2 lecture. Okay. Week 1 assignment questions are still due, so that cannot be discussed today. That's why I'm moving on with the revision questions. So week 1 assignment will be discussed next week. Now, so week 2 lecture was based on conservation of mass, then zeroth law, first law, and um, related terms of those laws. Okay. So first it started with conservation of mass. So conservation of mass, we have um, sort of heard about this in lower classes as well, where we say that okay, mass of a system remains constant unless mass enters or leaves. Right. That is the very layman approach of describing this law. But how mathematically we can incorporate it when we are discussing about the calculations or thermodynamic problems that we will encounter in future classes. That is what we are going to see now. Also, these various types of flow system, how this mass conservation will be coming into play when we are dealing with those things will be discussed. So okay, so I'll be starting with the derivation first of all. So here first itself we have to discuss something like a okay, like a duct or a pipe where flow is happening across the diameter or the cross circum I mean, the cross cut of this pipe. So this plane I am describing it as the cross section area of this pipe, and this I am sort of assigning the area. So it might be of a confusion, so I'm leaving this arrow over here. Take something else over here. Okay, so this is a cross section of this pipe, and I'm assigning area dA to this cross section, and it is sort of having a normal direction like this n. So I'm taking a unit vector n cap here. One second. Okay. Okay. So for this flow, so there's a fluid element, okay, that is sort of entering this system. Fluid element is having again a velocity v, and it is having a length l and delta l, small length. So it is approaching this cross section area. Now, how to sort of understand how this flow element is crossing this cross section? So for that, we are assuming this dA as this is the plane of that cross section dA, and then you have got this velocity vector v over here, and this plane is having a normal n. Okay, this I am taking as a not as a unit vector but a normal vector. So normal vector is the vector which is normal to the plane of the cross section. Okay. Now we have to resolve this velocity vector. So how to do that? Okay, I'm taking this. So there is one component of v which is along the plane. I'll take it as vp, and then there is this one component of v which is along the normal, that I'm taking as vn. Okay, so this vn component of velocity which is aligning along the normal of the area element or the cross section plane of the pipe, that is what is actually taking this velocity into the flow element into the cross section. Like for example, think about a velocity which is like this. Okay, it is not going to take the element into the pipe, right? Why? Because in mathematical terms, if we have to describe what we intuitionally understand, you have to say that the velocity component along the normal direction of cross section of this pipe is zero. Okay, or otherwise we will be saying it is v dot n equal to 0. Okay, that means v dot n is n v cos theta, where theta is the angle between this v and n. Okay, so if cos 0, that is this theta angle is 0, that means the whole velocity with which this element is entering, that is normal to the area cross section, and that is sort of creating this flow into the pipe. So that is how we will be measuring the flow. So nv cos theta, if that will be the v dot n component. So this v cos theta is what we are describing as vn component. Okay. Now, now we have to talk about flow rate, the element flow rate of the fluid element. So that flow rate, I'm taking it as d m dot, and that can be described as so first of all, d m dot is a small change in this flow element, the mass of the fluid element with respect to time. That is rate that we are talking about. This dot represent rate. 1 second. Okay. Okay. Dot represent rate of the uh, this mass. This m is mass of the fluid element. Okay. Now that is limit delta t tends to 0, delta m by delta t. Okay. So this you know that, okay, this is what dm by dt is what is written over here as dm dot. So that is equal to change in mass per change in time. Okay. Now this delta m can be written as what? Delta m equal to rho times delta v, change in volume. Okay, this is volume. This is density. So this can be again, this delta v can be written as delta L times delta A. This is area. This is length. Okay. Now, uh, combining all this thing, we can write delta M equal to rho delta L times delta A. Right. Now, if I take this delta M expression to the limit, then we will be getting dm dot equal to limit delta t tends to 0, delta L delta A rho by delta t. Okay. Now this delta A is the area of this cross section, right? So that I can take it out because that's a constant. Rho also I can take it out. So now what remains is limit delta t tends to 0, delta L by delta t. Okay, one second. Yeah, tell me, is there any query? You can type and then raise your hand, okay? So, yeah, so delta L, delta A by rho, delta T, that will be changed to this limit, and then that is like what? Change in distance by change in time. That is what is called as velocity, right? So which velocity we have to take here? As I have described earlier, the velocity which is along the normal of the um, cross section, that is what is going to create a difference, right? It is going to define the flow. So we have to take velocity as Vn. Okay. So in vector form, again, this Vn, I told you earlier that this is the um, sort of effect of Vn that can be shown in the vector form. So that you can write it as rho delta A V dot n. Okay. So this is how we will be describing dm dot, or the rate of mass flow. Okay. So this is one expression. In common terms, when V is like completely aligned to the normal of the cross section, then we can simply write it as m dot equal to rho VA, where V is volume, sorry, V is velocity, and A is area of cross section. Okay, so this will be the final expression. Yeah. Now, conservation of mass can be thought of in two different directions. One is control mass. So, conservation of mass, it can be dealt in two ways. One is control mass system, and another is control volume system. Okay. So control mass means what? Mass of the system is constant. That means there is this whole thing, this expression that I have written over here, rho del A V dot n. So instead of n, you can use the area element. Okay, area element also, because this n will be, n vector will have the magnitude of dA vector. Okay, so you can use it interchangeably also. Okay, so that is equal to that is what is dm dot, that is equal to 0, right? So dm dot is 0, so rho cannot be 0, del a cannot be 0, so that means v dot n is equal to 0. That is what we can derive from control mass system. So in control mass system, if I say that conservation of mass should be applied, then you can take v dot n, that is velocity of fluid element across the cross section. That is the flux of the mass flux equal to 0 across the boundary. That is the basic concept. So mass flux across the boundary is zero in control mass system when conservation of mass is applied. Okay. Now you have got control volume approach. For that, we have to think elaborately. So I'll take this as a separate section. So control volume. So there is this diagram of so this is a boundary of a system. You can take it as a duct or anything that you want. So this rigid boundary means what? This is the control mass system, right? Control mass system. Now now I am taking something like a dotted system. Okay, drawing over here. Okay. Mm. Now in this, I am assuming there is some kind of a gas or fluid working substances here. Okay, working substances present inside this system. Okay, it can be air or liquid or whatever it is. Some working substances present inside this pipe or duct. Okay, now I'm thinking about a fluid element. Okay, first of all, okay, this dotted boundary or dashed line will represent control volume. Okay, this is control volume, and then this is control volume, and now I am defining two scenarios. One is mass entering the system, another is mass leaving the system. Okay, so mass entering will be shown like this. So there is a mass element entering the control volume. Okay, why it can enter in control mass system? You cannot take any fluid element inside because it is a physical boundary. It is closed boundary. It is a closed system. In control volume alone, you can sort of create this kind of a change in mass, or you can let the matter enter or exit the boundary. As per the last class, if you remember, you will understand that in only in control volume system you can add or remove mass or matter. Okay, so here also, okay, 1 second. So here I'm first thinking about um, a mass element entering. Here I am thinking about a mass element exiting. Okay, in this control volume. Yeah. So this is a mass element delta M at inlet. This is a mass element delta M at exit. Okay. So this is exiting. This is entering. So this is control volume as I have told you. Okay. So this is at t equal to t1. Okay. This element is entering, and at t equal to t2 element is exiting. Okay. Now let me tell you that this is state 1 and this is state 2. Okay. Now at state 1, how can we write the mass of control control mass. The whole control mass means you have to think about the boundary of the physical boundary that is shown over here in bold line. So mass of control, this control mass system, mass can be given by what? MCM equal to this delta Mi, which is entering the control volume, which is having MCV at time equal to T. Okay. Now, similarly, this control mass at of state 2 can be given as what? Okay, this is state 1. So at state 2, what will happen? MCM at 2 equal to delta ME plus MCV times T. Again, you can see control volume. This mass is, I'm taking it as the same mass, this constant mass. So that is not changing. But this element that is entering and exiting, that I am taking as two different, uh, different mass. Okay. Now, if I say that, as we know, control mass, the mass won't change with time, right? In control mass system, mass won't change with time. So this equation 1 and equation 2, from here I can say that m of 1 control mass will not change. That means it will be equal to control mass of state 2. Okay. So mass of control mass of state 2. Okay. Now if I equate this equation 1 and equation 2, what will I get? Delta m delta mi equal to, delta mi plus this term. Okay. Plus delta m cv comma t equal to delta me plus delta m cv comma t. Okay. Okay, sorry. So here control mass will change with delta t, right? So this is t, t2 is t1 plus delta t. Okay, sorry, forgot about that. So delta t. Okay, so t plus delta t. So what will happen over here? I can rearrange the terms and I'll get what? Delta. Okay. So I'm sort of taking a limit with respect to t for all the terms. That means I'm dividing, and I'm dividing it by t first of all. Delta t, change in time. Okay. And then I'm taking limit delta t tends to 0. I am assuming this delta mi by delta t becomes d. Sorry, I'm just taking this as mi dot, that is flux of mass entering at inlet, and delta me by delta t is the rate of mass exiting at the exit. Okay. So this I am writing it as me dot. Okay. From equation 3, I can write it as mi dot plus this whole term. Okay, this term I'm taking this side. Okay, and I'm taking this to this side. I'll be getting mi minus me dot equal to delta m cv comma t plus delta t minus delta m cv comma t by delta t. Okay. So this is equal to 0. In other words, we can say M, okay, Me dot minus Mi dot equal to the other way around, right? So this term I can take it as um, d by dt of mcv. Okay, so I'm taking it as mcv. So here it will come as dy dt of m. Okay. Me minus mi equal to, yeah, minus mcv. Okay. Or if you take it all together, it will become d by dt of mcv equal to 0. So this is the final equation for conservation of mass in control volume. Okay. So if there are multiple inlets and multiple outlets, then you have to sum it across all the inlets and outlets. So it will be coming like over all the exit will become m dot e minus, okay, summation of m dot I over all the inlets plus d by dt of change in mass of control volume with respect to time equal to 0. Okay. So this is widely, known as continuity equation. Continuity equation or conservation of mass equation. For a control volume. Okay. Now, next up is flow work associated with mass flow. So flow work is, as you know, in the system you can see there is some working substance filled inside this system, right? So this substance is exerting some kind of a pressure, right? Pressure over this walls. Okay. So for here also, if you are considering a area element of cross section, in this area also there is some kind of a pressure being exerted. Okay. So that pressure, you if you have to let any matter inside, you have to work against that pressure. You have to push that fluid element into the system against that pressure at that point. So that pressure, um you can quantify it as force using this equation, right? So I'll start with flow work. Flow work. So flow work means what? Flow work means there is this element delta mi that I'm taking, that is to be introduced into a control volume or into a system. So that system is already having a pressure pi. Okay, pressure pi at inlet, and this area is dai. This area is dai. It's the area of cross section. Okay. So now, if I want to make this element enter into the system without any acceleration, the net force should be 0. So what is the force required? Minimum force required to push this element into the system? That will be Fi, which is equal to Pi times dAi. Okay. So if this element is having a um, length of DLI, I can say that work done on this element to, sort of make it enter into the system will be delta Wi, which is equal to, it is work done on the system, that is why negative will come. Then Fi is the force that is used to push this element into the system, and the length or the displacement will be DLI. Okay. Now this Fi, I can write it as this one. Pi dot DAI times, negative will be there, DLI. Now I can rearrange it. So I'll be getting dA volume. So it will become Pi times delta Vi. Okay. This volume I can write it as mass by density. So that is equal to Mi, sorry, delta Mi, that is the mass of the element, by rho. So yeah, because Mi by Vi equal to rho, right? So, so this 1 by rho I can write it as specific volume, right? Specific volume Vi delta Mi. So this is specific volume. Okay. So this is the final expression. Sorry, this is not rho, this is P. P is the pressure. So this is pressure. This is mass of the fluid element and specific volume. Okay, this is the work required to make this element enter into this system. So this work is called flow work. Okay. So the minimum work that is to be done against this pressure force to push or push in or push out this fluid element is called as flow work. Okay. Now, so next topic will be, okay. So these things are discussed. Yeah, zeroth law of thermodynamics. So, zeroth law of thermodynamics came long after first, second, and third, and this was very fundamental in nature. That is why it has to be placed as zeroth law of thermodynamics. So it is based on something which we say as calibration. Okay, very basic way how we are measuring our calibration. Okay, measuring any of the things around us. For example, our scale or length, a unit of measuring length is calibrated into something which is called as a standard unit. So that standard unit is derived from something which we so fundamentally believe as very basic or fundamental. So that is how we are calibrating something. Like for example, mass is also, we have this 1 by 12th of carbon atoms mass will be taken as 1 unit of mass, and then from there we are deriving all the units of mass. For even for time also, we will be having some sort of a absolute phenomena that will be taken, and then we will be calibrating everything that we have for measuring to that sort of standard unit, and then we will be measuring, right? Likewise, for temperature, for in thermodynamics, that the idea of calibration is sort of described in the form of zeroth law of thermodynamics. So only for temperature, we this calibration is termed as zeroth law of thermodynamics. Somebody, one second. Nobody is here at the waiting room. Okay. So, zeroth law of thermodynamics states that if two systems are in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. That means if system A is there, system A is there, system B is there. Okay. So, system A is in thermal equilibrium with system C. Okay, that is the third system. Also, system B is also in thermal equilibrium with system C. Thermal equilibrium means what? If there is a thermal sort of like non-equilibrium exists, okay, then what will happen? Then there will be heat flow happening, right? That means what? Heat flow is what? Heat flow is due to temperature difference, okay? It is due to temperature difference. So if there is no heat flow happening, that means the temperature is same. That means it is in thermal equilibrium. Okay, so if A and C are in thermal equilibrium, that means there is no heat flow that is happening. So heat is not there. That means there is no temperature difference. That means A and C are in the same temperature. So if this TA is there, TC is there, TB is there. So if A and C are in thermal equilibrium, that means TA equal to TC. Then if B and C are in thermal equilibrium, that means TB equal to TC. That means by zeroth law of thermodynamics, it says if two systems are in A and B are in thermal equilibrium with the third system, then they are also in thermal equilibrium with each other. So TA equal to TB. So this is very fun. We intuitively sort of understand this concept, but when it was stated after all this first law, second law, third law, because this is very fundamental that they thought, okay, they will state it as a zeroth law. That is why we have to study this thing. Where this application is happening is for basically thermometers. Okay, so thermometers use a standard reference point, which is usually the triple point temperature of water. Triple point temperature means what? Where ice, water, and gas or vapor form coexist. Okay, so water, three phases of water coexist at coexist at triple point of water, which is at 0.101325 bar and 0.01 degrees centigrade. So if pressure is changing, then this temperature will also change. So that is why pressure and temperature, as we know, two intrinsic properties are required to fix a state. That's why pressure and temperature is mentioned for triple point of order. Okay, so this is practically taken as a standard reference point. Then another reference point that we have is steam point. So steam point is vapor liquid equilibrium. Okay, so this happens at what? This happens at, again, pressure is 0.101325 bar and temperature is 100 degrees centigrade. Okay, so this is steam point. So these are the two reference points for thermometer calibration. Okay. And then we are talking about temperature scale. So absolute thermodynamic scale is Kelvin. Thermodynamic temperature scale is Kelvin. Again, how to write small k, unit is Kelvin, capital K. And we usually use degree centigrade, which is Celsius scale. Celsius scale is um, Kelvin minus 273.15 gives Celsius, degree Celsius. Okay. So this is what is zeroth law. So zeroth law sort of gives a idea about how to measure temperature, and then only we can go for internal energy or other forms of energy measurement, calculation, etc. So that is why zeroth law is very important. It sort of lays a very base or foundation of all our discussion. Now, first law of thermodynamics. First law of thermodynamics says that in a cyclic process, okay, so first law of thermodynamics is basically energy conservation law. Okay, that means this is a very common way of stating that. What we have to say is it sort of states that in any cyclic process of a system, we are referring here control mass system. Okay, control mass system or a closed system. Then cyclic integral of heat is proportional to cyclic integral of work. Okay. So means what? In a cyclic process of a system, think about uh, property coordinates P1 and P2. Okay, P1 here, P2 here. You have got uh, state 2 and state 1 over here. Okay, which is of P1 of 1, P2 of 1, and here it is P1 of 2 and P2 of 2. Okay, now this cyclic state means what? It is going from 1 to 2, and then from here 2 to 1. It is coming back. Okay, so this is a cyclic process. Okay, in the cyclic process, it is already said that it is a control mass system. That means mass is not going to change. Only energy transaction is happening. So somewhere heat is added, then somewhere work is added or removed. Okay, so heat is added or removed and work is added or removed. That is how you are going from state 1 to state 2, and then coming back from state 2 to state 1. Okay, so in the first law says that, so this addition of heat that is happening, cyclic integral means over this entire cycle. That means this is path A and path B. So path A to path B. Okay, this entire path, whatever change in heat is happening, or heat, yeah. So whatever heat is being added or removed is going to be proportional to whatever work is obtained or given to the system. Okay, this is cyclic integral. That means it is the path along the path of the process we are integrating this work and heat. Okay, so if for example there are several works, several path happening, like suppose there is five states are there. Okay, so you have got again property chart I am drawing, and you have got 1, 2, 3, 4 and 5. Okay, so state 1, so this is P1, P2, two intrinsic properties are there. State 1, state 2, state 3, state 4, state 5 is there. So there is one path, then there is second path, there is third path, there is fourth path, and there is fifth path. Okay, so this is a cyclic process, right? So if I'm saying the entire delta Q is going to be so cyclic integral of heat is equal to what? Cyclic integral of heat from state 1 to state 2, whatever heat is added or removed, that we don't know. We just know that change in so there is some heat is in transit. Okay, some flux is happening of heat energy, so that we are taking it as delta Q. It can be positive or negative, that we don't know. So that you are taking it as along the path from 1 to 2. Okay, 1 to 2 plus from 2 to 3 delta Q, then from delta Q integral 3 to 4 plus delta Q integral 4 to 5. Okay, so this entire thing gives delta Q over the entire cycle. The cyclic integral is given by individual path integral of delta Q. Okay, so this can be written as in this way also: Q12 plus Q23 plus Q34 plus Q45. Okay, this is the easiest way of representing this integral over path 1 to 2, 2 to 3, etc. Okay, now similarly this can be written for work also. So how to write it for work? Again, delta Q, sorry, delta W is equal to, so I'm just writing this W1 to 2 plus W2 to 3 plus W3 to 4 plus W4 to 5. Okay, now it says delta, this entire cyclic integral of heat is equal to cyclic integral of cyclic integral of work. So proportionality something should be there, that should be taking it as K. Okay, some value is there. Okay, now in SI unit this K is taken as 1. Okay, like after experiments and calculations and everything, this when we are converting Q and W in SI unit, if we are taking, then K is also 1 in SI unit. So this becomes regular equality. Okay, this is first law. Okay, now we have to think about what is exactly happening in this process. Okay, so for that we are again considering, should I write okay, derivation I'll write separately. So first law, thermodynamics. Okay, first law So I'm uh, going to draw two processes. Okay. So this is P1, P2. Two intrinsic properties are there for defining two states, 1 and 2. So what is happening is I'm taking this one system from state 1 to state 2 through, okay, through this path. Okay, one path I am defining. This is how I am taking one one system from state 1 to state 2. Okay, this I am saying it is path A. Okay, now there is uh, it can come back to 1 through any path. So I am taking one path is this. So this is path B, I'm saying. So what is happening in from A to B? What is happening? So let's take A and B combined together. So this cyclic process I am considering right now. So from 1 to 2, there's a state change that has happened through the process of so through the path A or the process A, and it can be reversed, or it can be retained back to state 1 through path B, or again you can retrace it back through path A itself. Okay, for the sake of showing the calculation, I am taking another path. So what is happening in this cycle AB? Cycle AB, this as we know from integral cyclic integral of heat is equal to cyclic integral of work. Cyclic integral can be written as so over path A, okay, from 1 to 2. If I take delta Q, then over path B, delta Q is there. So from 2 to 1. So from 1 to 2, okay, from 1 to 2, this delta Q I am calculating. Then again from 2 to 1 over path B I am calculating delta Q. Okay, that is equal to, again for work, I can take from 1 to 2 delta W over path A plus from 1 to 2 to 1 over path B delta W. Okay. So this is one equation that I'm getting. Hmm? If I think about another path, okay, I can take this system from state 2 to state 1 in multiple ways, right? So I'm thinking of another path here, which is path C. Okay, and I'm considering the cycle AC over here. Then again I can write the same equation, but instead of B it will come C, right? So I'll write 1, okay, over path A from 1 to 2 delta Q over path C from 2 to 1 delta Q equal to delta W integral over path A 1 to 2 plus integral delta W over path C from 2 to 1. Okay. Only in place of B it became C. That is the only change that has happened. Okay. Now subtracting these two equations, this ones will go, right? These will go away and you will be getting 2B minus 2C sort of equation. So equation 1 minus 2 will give integral delta Q over path B from 2 to 1 minus integral uh, delta Q over path C from 2 to 1 equal to integral delta W over path B from 2 to 1 minus integral delta W over path C from 2 to 1. Okay. So every we are just taking this 2 to 1 because that is the only change that is happening. Whereas for both the cycle, it is going from 1 to 2, sorry, 1 to 2 over this A path itself, right? So this part got subtracted off, and you are only calculating the change of the system when you are coming through path B and path C. Okay. Now you can merge it and write like from integral of okay integral of delta q minus delta w over path b from 2 to 1 equal to integral of delta q minus delta w over path c from 2 to 1. Okay. So this quantity delta q minus delta w over C and B, path C and B, that integral is going to be constant or it is same. So this, that means what? This delta Q minus delta W quantity, no matter whichever path you take, it is going to stay constant. So it is path independent. So this delta Q minus delta W, okay. So this delta Q minus delta W is path independent quantity. Okay. So any path you are taking, this is not going to change. This path independent quantity is called a point function. That means it doesn't depend on the path, but it depends on the point of calculation, like from 1 to 2. So 1 is a state or a point, then 2 is a state or a point in this property coordinates. And what is happening is, unless you change these 2 points, no matter which path you are taking between the points, it's this quantity of delta q minus delta w is not going to change. So this point function is a property of the system because you know that any point is state, that state is defined by this property of the system. So this delta q minus delta w is also a property of the system. That property is energy of the system E. Okay. This is that property that we are seeing. So we can write delta q minus delta w equal to delta E. Okay. This is how we are getting first law of thermodynamics. So first law states cyclic integral of heat is proportional to cyclic integral of work in a cyclic process happening in a closed or constant mass system. Okay. So that from there we are deriving it that okay, there is this change in heat to change in heat and change in work. If you are sort of taking the difference, you will get the change in energy of the system. Okay. So if I say that from change in energy is what? So energy at state 1 is E1 if I'm taking. Energy at state 2 is E2 I'm taking. So change in energy is E2 minus E1. Okay. Change in energy is E2 minus E1. Then this Q, I know that okay, this is how we are writing 1 to 2. Right. So this is how we used to write. So that will be written like this: 1 to 2 equal to E2 minus E1. Okay. So work and heat are two path dependent properties because you cannot calculate uh, this is you cannot calculate work, okay, work or heat without knowing the path. Okay, if I am taking uh, path B, that work will be different. Path C, the work will be different. Path B or C, the heat will also like vary. But energy, it doesn't depend on the path. Now again we are talking about energy. We will come to the topic of internal energy, kinetic energy, potential energy, which was discussed in the last class. So what is energy? Energy is the energy of a system. Okay. Energy of system is the sum of E equal to sum of internal energy plus kinetic energy plus potential energy. So kinetic energy, again expression if we are writing, it is half mv square. Okay, so half mv square. Potential energy is uh, fdz, or you can in gravitational field it is mgdz, where z is the normal height from the potential field. Okay, so combining all this thing, we can write dE, that is change in total energy of the system, equal to change in internal energy plus I'll just write everything d de sorry du plus m m v dot dv. So this is v square, I'm writing it in this form, plus mg dz. Okay, so this is the energy equation that we are seeing in by 2. Now we will discuss something called as specific energy. Specific energy is per mass, per unit mass. So specific energy is the intrinsic property. So this is extrinsic, and specific energy is intrinsic property, which can be taken by everything divided m if I'm doing v dot dv by 2 plus g dz. Okay, so this is small e. Okay, de equal to d small u plus v dot dv by 2 plus g dz. Okay, we generally take this whenever we are mentioning something specific. Okay, so in next up we will be seeing another quantity, enthalpy. So there also we will be saying specific enthalpy. So enthalpy is mentioned as h and specific enthalpy is small h. So that is how we will be defining the quantities, like denoting these quantities. Okay, so specific energy, internal energy. So du de, how to write these things? E2 minus E1 is dE, equal to U2 minus U1 is du. So this is specific internal energy. Okay, then this is specific energy plus half V2 square minus V1 square, that is change in kinetic energy, specific kinetic energy, because m is not here. Okay, then we have got potential energy. Okay, specific potential energy because m is not there. Okay, this square we are taking. So see, I want to calculate velocity change, right? So I d v square I am taking. Okay, dv square I am taking, that will be 2v dv. Okay, that is what I'm writing it here. So V dV. Okay. Yeah, so enthalpy. Now next up is a quantity called enthalpy. So before that, we will again go back to this equation. Okay, this equation we will take. Okay. So I hope you are understanding the discussion till now. Okay. So consider a closed system undergoing an isobaric process. What is an isobaric process? It's a constant pressure process. Okay, constant pressure. Okay. So constant pressure process in which pressure is constant throughout and expansion of gas in a piston cylinder arrangement is happening. Okay. So this is a closed system. So this is piston. Sorry, this is cylinder. This is piston. So constant pressure is being applied. P is constant. And then expansion of gas is happening. So volume is going to increase. Okay. Expansion is going to happen. Okay. Now, so first law. So what is first law? First law will say Q. We'll write it with. So Q from 1 to 2. So there is this first state is piston over here. This is 1 and this is 2. Okay. 1 to 2 equal to W1 to 2 plus E2 minus E1. This is first law. Okay. Then, so if I'm saying that this piston is moving with a constant velocity and uh, and there is no change in elevation or anything. That means constant velocity means no change in kinetic energy. Delta KE equal to 0. And then I'm saying there is no change in elevation of the system. So system is staying in the same ground state. You're not thinking about the piston over here. Piston distance and change and all those things we are not thinking. We are thinking about the system, the whole system. Okay. So there is no change in constant Z. Okay. That means delta PE is also 0. That means E is U plus KE plus PE. So PE is 0, KE is 0. So E equal to U. That means total energy of the system is internal energy only. So from here it will come Q12 equal to W12 plus U2 minus U1. Okay. This became like this. Now W12 we have to find. Okay. So what is W12? As I have told earlier, that is flow work over here. What is flow work? Flow work is pressure times change in volume. This one. Okay. This right here I am taking pressure times change in volume. So that is flow work. So flow work W12 is equal to integral 1 to 2 P dV. This is volume, okay, and this is pressure. Okay. Now this P is constant, so we can take it outside the integral. So this will become dV equal to P V2 minus V1. Okay. So flow work W12 we found. Energy we found it is just change in internal energy. So Q heat from 1 to 2 is P V2 minus V1 plus U2 minus U1. Okay. that is equal to PV2, just expanding the bracket terms, plus U2 minus U1. Okay. Now taking all the 1 and 2 subscripts together, it will become PV2 plus U2 minus PV1 plus U1. Okay. So again you are seeing some quantity over here which is like changing from state 1 to state 2. So state 2 is having this U plus PV. State 1 is having U plus PV. So this is PV plus U of state 2 minus PV plus U of state 1. Okay. Now if I'm saying that okay this is internal energy, so I have to talk about specific uh, specific internal energy. So what will I do? By by m I am dividing the whole term. PV plus U by m 2 minus PV plus U by m of 1. Okay. So divide by m means V by m is specific volume, right? So P small v plus U by m is small u. That is specific internal energy. Specific volume, specific internal energy. Okay. Of 2 minus P V plus U of 1. Okay. Okay. Now this PV plus this I am multiplying and dividing by m. Okay. Otherwise this will be wrong. Okay. So this m times this bracket quantity, that quantity I'm taking it as something called H. Okay. H is, so if I'm not talking about specific here, then this is how it will be termed as. This is called enthalpy. Okay. So enthalpy H is given by U plus PV, or specific enthalpy is given by small h, which is P V plus U. Yeah. This is specific volume and specific internal energy. Okay, now H and U are having the units of SI unit is joule. Okay, because enthalpy is also a measure of energy. So PV is flow work or flow work, which is having unit of energy. Internal energy is again unit of energy only. Okay. So this enthalpy will also have SI unit of joule. Okay. Or now so that's about first law of thermodynamics. Now we have to talk about how to apply this law into our system. Okay. First we will talk about open system. So first law, one second. First law of thermodynamics. In open system, so how to derive that expression? Again, we have to go to our control mass approach. Okay. Okay. This I am taking. So as we know, we were calculating an element entering and also an element exiting. Okay. The control volume, because it's an open system, right? Open system means both energy and mass can uh, enter the system and exit the system. So here I am thinking about some energy entering the control volume. Okay. So okay. So this energy, change in energy at the inlet is taken as EI, delta EI, and change in energy at exit is taken as delta EE. Okay. And the system at T equal to T2, which is T2 is equal to T1 plus delta T, and this is at T equal to T1, and this is having an energy of control volume as ECV at T. This is ECV at T plus T1 plus delta T. Okay. Now, in control mass, we are calculating the energy of control mass. Energy right over here. Energy of control mass at state 1 is ECM of state 1 equal to ECV of T plus delta EI. Okay. Control mass means this entering element will also be included. Then energy of control mass 2 is ECM of 2, which is equal to ECV of T plus delta T plus delta E of E. Okay. Now, this delta EI is energy of the element at inlet. Okay. So that you can take it as a small system by itself. That will be what? Energy of element at E1 at inlet is equal to delta EI equal to uh, internal energy plus kinetic energy plus potential energy, right? That is equal to. So so this internal energy, so sorry, this delta EI can be taken as specific total energy, that is total energy by mi, that is the mass of the element. Okay, that also you can take it in this way, that is equal to specific internal energy plus velocity of the element entering plus potential energy times delta mi, or directly also you can write it as capital U I plus uh, mvi square by 2 plus m gzi. Okay, this is also one way of writing. This is like you are taking this mass outside for ease of calculation for later on. Okay, that is why I have written it in this small specific units. Then similarly, delta EE also can be written as delta ME UE plus VE square by 2 plus GZE. Okay. Now, so next up is in the first law, we know Q is there, W is there, and E is there. So for work calculation, we have to think about um, work that is in this control volume. I mean, work is not contained inside the control volume, but there is some work that is being transferred into the control volume through mechanically or electrically or Thermally we will be taking it as heat, but mechanically or electrically you can or magnetically you can give some work. For example, in a controlled volume, if I'm stirring, if I'm mixing something using a spoon or something, that is called stirring. So that stirring is a mechanical way of providing work into the system. If this system is giving that work out, like for example this piston cylinder system that we were talking about, uh, like in our IC engine, that is a piston cylinder system, right? And that is connected to a shaft. That shaft is rotating. That is a way of the system giving work as an output. Okay, so this different forms of work like shaft work or electrical work and all those things, that we will be taking as delta W of CV, control volume. Then at inlet there is a work for entering this element, and outlet also there is some work which is like pushing out the element, that is giving out of the system. That's why I am taking it as positive. Okay, so this is W. Again, W, we know we are taking it as flow work. Flow work term. So flow work term is delta Wi equal to Pi, then specific volume Vi times delta Mi. Okay. Or you can take it as rho AV also. Sorry, Pi delta V also. I am taking it in this manner. Sorry, not specific volume, this is velocity. Okay. Then for exit again, this will be PE, VE, delta, ME. Okay. For outflow. So this is inlet or inflow, and this is outflow. Okay. Now we can apply this first law of thermodynamics. It will be coming as Q12 equal to W12 plus ECM of 1 minus ECM of 2. Okay. Or the other way also, like because it's changed, so in final state minus initial state, that is also possible. Okay, final state minus initial state. So heat transfer process, if I'm saying, so heat is transferred to the control volume. So I can take it as QCV. So QCV equal to okay, this W, I have taken this in this manner, right? Delta W. So that I have to write. W12 is delta WCV. Then instead of WI and WE, I have to write these terms. Okay, flow work of inlet and outlet. Okay, so this is W12. Okay, then my okay, plus yeah, plus what is E1 and E2? E1 and okay, E1 and E2 are the control volume terms that we have taken. So this is what we have to write. Okay, this term. This term we have to write for EI. This term I have to write for EE. Okay, so that comes from, or I'll write it again. So this is E CV T plus delta T plus delta EE, that is ECM of 2, then minus ECV T. So this term is this term, ECV of T minus sorry plus delta EI. This is ECM of 1. Okay. Now expanding this ECM of 2 and ECM of 1, I'll be getting QCV equal to QCV equal to delta WCV plus okay, delta WCV plus EE plus PEVE delta ME. I am just trying to okay, this term has got delta ME and EE, so ECM. Okay, this term, this is EE delta ME. Okay, this is what I have combined together. Similarly, these two terms, this term and this EI delta MI, I'm combining. Okay, so that will be okay. So there is plus and minus. Okay, this is plus and this should be then minus, because here the minus term is here. So minus EI plus PI times small delta MI. Okay, then the rest of the term. What is the rest of the term over here? This term and this term plus ECV comma T plus ECV comma T plus delta T minus ECV comma T. Okay. Now this EE I can expand. Okay, EE and EI I can expand. So that will be internal energy plus kinetic energy plus potential energy. Okay, that when I'm expanding, I'll be getting QCV equal to delta WCV plus this EE I'm going to expand. So EE equal to UE plus VE square by 2 plus GZE plus then this term PE VE times delta ME. Okay, then this term next up is minus UI, sorry, small u I have to say, UI plus VI square by 2 plus GZI plus then this term PI VI times delta MI, then this term I have to write plus E CV comma T plus delta T minus E CV comma T. Okay, now you can see there is this U plus PEV term in both the bracket terms, U plus PEV, UI plus PIVI. So that will become this U plus PV equal to H. Okay, that I am going to rewrite. So QCV equal to delta WCV plus HE plus VE square by 2 plus GZE delta ME. Okay, then minus HI plus VI square by 2 plus GZI times delta MI. Okay, then this term plus ECV T plus delta T minus ECV comma T. Okay. So this thing I can write it as DECV by dt. Change in internal change in total energy of the control volume with respect to time. Okay, with time it has changed, right? So this I can write it like that, and these terms are combined already. So now the final sort of the equation will be like this: QCV equal to WCV. So I am taking all the changes. Okay, this was delta QCV. So yeah, all the changes is some sort of rate of change I am taking. Here also with respect to time I am taking. That's why everything I am writing it as rate of change of heat transfer and work transfer, etc. is equal to. So here it will be flow rate will be coming. So me dot t, me dot and mi dot will be coming. Okay. So now this will be he plus ve square by 2 plus gze me dot minus hi plus vi square by 2 plus g zi times mi dot plus decv by dt. Okay, this is the final equation. Okay. Now for multiple inlet and multiple outlet, you have to do the summation over exit or exit and inlet. Okay, that will be the only change happening for multiple inlets and outlets. Okay, so this is the final equation for open system. Open system means where mass flow and energy flow is happening. Now another thing is for steady state. So for steady state, how will the whole equation change? So with respect to time, what all things are changing? So first law, okay, first law for open system steady state. Okay, in steady state, first we have to every problem starts with conservation of mass. Then we will go for conservation of energy. That is the first law of thermodynamics. So for conservation of mass, what we have learned, conservation of mass or the continuity equation, it was like okay. So rate of flow of mass over the outlets minus rate of flow of mass over summed over inlets plus d by dt of mass control volume mass is equal to 0. Okay. Now in steady state, what will happen? Control volume mass is not going to change with respect to time. That means this mass exiting is going to be equal to the sum of mass entering. Okay, this is what we are going to get from conservation of mass. Now, conservation of energy or the first law says what? Q dot CV plus summation of enthalpy, kinetic energy, potential energy of the inlet flow is equal to WCV plus summation of enthalpy, kinetic energy, potential energy of outlet flow. Okay. Then plus change in internal energy of the control volume. Okay. Sorry, change in total energy of the control volume. So total energy of the control volume is going to be affected with the work in input and output, then heat input and output, and the enthalpy change, kinetic energy change, and potential energy change over inlet and outlet. Okay. So this is what is stated by conservation of energy law. Now you can see steady state means there is no change in total energy of control volume with respect to time. So d by dt term will go to zero. So you will be getting this uh, equation in steady state. So that is the only change. Steady state means any change with respect to time is going to be, that term can be neglected. Okay. Now for transient system, what will be the change happening? This term should be included. Okay, that is the only change that is happening. Okay, so that's about the revision. Now let's go to the problem solving. Okay. So revision questions we'll just take one by one. Okay. Yeah. So what's the first question? First question is, which of the following statements are true? Okay. So heat is a property of substance. False. Heat is energy transit that is happening across the boundary of the system. So this is false. Okay. Heat is not a property. Temperature is a property. Heat is not a property. And heat can be stored in the body. Again, no, it is false. Why? Because heat can be measured only across the, heat is observed only across the boundary of system. Observed only at boundary. Okay. Now heat is only at the boundary of the system. That is true. That is what we have explained in the second point. So heat is energy transfer across the boundary of a system. So yes, it is observed only at boundary of a system. Now we cannot talk of heat or work if we do not define the system boundary. True. Why? Because these are observed only at boundary. So if we don't define system boundary, then we cannot talk about heat or work. Work is not a property of the body. That is true, because work is also just like heat. It is observed at boundary. It is not a property of boundary. It is the energy interaction that is taking place across the boundary because of the change in state of a system. Then electric power consumption is a form of work. True. Why? Because any energy crossing the boundary, any energy uh, crossing the boundary, uh, if not due to temperature difference, is work. Okay. Now definition of heat. Heat is okay. Definition of heat. It is energy transferred across boundary due to temperature difference between system and surrounding. Okay. Now 2.3. Comment on the statement conservation of mass can be applied only if there is a steady state. Uh, that is not correct. Why? Because not correct. Because conservation of mass is always valid. Okay, conservation of mass is always valid in a microscopic state. Um, because mass can neither be created nor be destroyed, right? But in steady state, what is happening in steady state means accumulation of mass is zero. Accumulation of mass is zero. Okay, that is the only thing about steady state. In unsteady state, maybe mass of the system can change with time, but it doesn't mean that conservation of mass is not valid. Like in our equation, uh, okay, mm, in mi equal to dm by dt, right? Dm of cv. So steady state means this will become zero. So whatever is entering is exiting. That means there is no accumulation. Okay. But in unsteady state, what is happening? This d by dt term will be retained. That means what? Entering whatever is entering is not exiting completely. So that means there is some kind of a accumulation that is happening. If whatever is exiting is more than whatever is entering, what will happen? Then the mass from the system is also going out, right? So after some time it will be emptied. Okay, so that is also an unsteady state thing only because control volume mass is changing with time. Now next is definition of work. What is work? Work is a form of energy transferred across the boundary of a system that is not due to temperature difference. So the same sentence but just add not over here. Okay, so anything apart from the energy transfer occurring due to temperature difference is any work and any energy. Okay, note I have to just add no due to temperature difference. Okay, that is work. Now, what is meant by the term flow work? So, flow work is the energy required to 2.5. Energy required to um, push fluid in, into, or out of uh, control volume. Okay, out of a control volume. It is called flow work. Okay, it can be quantified using pressure times specific volume. Now, next is comment on the statement. Conservation of mass is same as conservation of molecules. Yeah, that is a very important question. So I'll just talk about this thing. So conservation, what is conservation of mass? Conservation of mass means total mass is constant in a system. Okay, total mass is constant means conservation of mass. Okay. Now, conservation of molecule means what? If you have got a system with these many number of molecules, then that is not going to change. That is not true, right? For example, conservation of molecule does not exist. Okay. Why? Example, you've got hydrogen plus oxygen giving water. Okay. So, what is the sort of okay? This is how you balance the equation. That means before the reaction there were three molecules. Okay, it's not three molecules. This three into three Na, right? Avogadro number you're talking about. This stoichiometry is three. Okay, just think about Avogadro number over here. Then you have got only two Na molecules after reaction. Okay, which is actually not holding this conservation of molecule idea because there is nothing called conservation molecule. But think about mass here. Mass, what is happening? You have got four hydrogen. Okay, so here before reaction you have four hydrogen and two oxygen. After reaction also you have got four hydrogen and two oxygen. Just compute the mass. It will be same, right? Hydrogen is 1. So 4 unit mass plus 2 oxygen means what? 2 oxygen means oxygen mass is 16. So 2 is 32. So it is 32 plus 4, 36. The other place also it is 36 unit of mass. So mass is conserved all the time, not molecules. Okay. So this is a counter example that you can give to say that okay, this is not how it works. Okay. Now next up is how can conservation of mass be applied to the reservoir produced by a dam or barrage on the river? Okay. Conservation of mass, how to apply is because it's the same thing. The equation you can write. What is it? Exit if you take minus inlet mi equal to dmcv by dt. So summation means like there will be multiple inlet and exit for dams. Okay, dam you have seen one shutter, two shutter, etc. It will be there. Several number of shutters will be there. If it is open, then it will come. The water will come out of the reservoir, and the same way, like river might have a lot of tributaries, so that will be coming and joining at the reservoir. So there will be multiple inlets also, or multiple check dams will be before this reservoir. So if you are closing one of the check dam, then that inlet is closed. That is how it works. So those mass which is being flow which is coming into the system, that is going to change the this control volume here is what? Reservoir. Okay. Change the mass or water in reservoir, the amount of water in reservoir. So this is how you can take conservation of mass equation to a real world problem. Okay. So that is why in rainy time this mi summation of mi term will be larger than exit term. So this dmcv by dt will be highly positive because it is going to increase in time. So change in mass of control volume is positive, means it is increasing, mass is increasing, that reservoir cannot hold this much water, that you have to increase me, right? You have to open the shutter so that water will flow out. Now why is electricity a form of work? So anything, any displacement of particle using force inside a potential field, enough potential field is called work. Okay. So electrical electricity is a form of work. Why? Because electrical energy is has to be there for moving a charged particle in a potential field. So electricity means a flow of electrons in a electric field, right? So flow of electrons in a electric field. So electric field is a potential field. Our electric field, we are taking it as a uh, potential here is due to potential difference. This field is there. That is why this flow is happening. So that is why we are taking it as a form of work. Now, there are only two forms of energy transfer in thermodynamics: heat and work. Is the statement correct? Yes. Why? Because see, another what all flux we will be considering: heat, work, and mass. So with mass, we have seen there is this total energy coming, which is like internal energy, potential energy, and kinetic energy, right? So this we are taking it as what? Enthalpy change. We have seen in our previous okay, that is in the other one. Okay, we have seen in the previous derivation that this energy change, this entire term is one term of energy. Okay, so heat is a form of energy, work is a form of energy, this entire thing is a form of energy, this entire thing is a form of energy, right? So whatever energy is associated with flow of mass is taken into consideration through enthalpy change. Or okay, so that is already taken care of. Now the other two form of energy transfer or energy interaction is just heat and work. So in that way, this is yes, this is correct. Okay. uh, Mass transfer, uh, energy change is computed or calculated using calculator is calculated using enthalpy. Okay. Now mass flow rate can be obtained from the formula rho AV only when only when okay, there were options also. I forgot to add that option. So 2.10 options are flow is normal. Okay, I'll just write the answer. So when flow is normal, then Vn becomes V only. Okay, so you have got a cross section area that is having n vector over here, dA area, and V is also normal. That means V dot n equal to Vn because cos 0 is 1. Okay, so yeah, flow is normal. That holds. That is one thing. Then density rho is uniform across the area. Otherwise, you have to integrate rho over that area element to find the total density. Okay, rho is uniform across area. Then third one is velocity is uniform. So V and the rho is uniform across area. That is when we are taking then steady flow, steady state flow condition, steady state. So these are the conditions. Now next one is work is defined in thermodynamics is work is defined in thermodynamics is same as work in mechanics of rigid body. Think. Yes, work is everywhere. It is defined as force acting through displacement, right? But in thermodynamics, we will include all kinds of field. Like in rigid body, we are only thinking about gravitational field. But in thermodynamics, we are talking about electrical energy, mechanical energy, magnetic force, and the work done by magnetic force. All those things we are talking about. So, concept is same, but the only thing is we are taking a broader perspective of work. Rigid body includes only mechanical work, thermodynamics, uh, covers all form of work, like all field, okay, all potential field, potential field, electric, magnetic, gravitational, etc. Okay. Now, give example of work associated with field, gravitational field, magnetic field, and electric field. Yeah. So, this is again gravitational field is what? You lift a mass, um, from ground. That is gravitational field work. Magnetic field means what? You you move a current carrying conductor in a magnetic field, or uh, electromagnetic induction. Those things are magnetic work only. Then electric field is what? Electricity is electric field work only. Like moving a charged, moving. Okay, charge moved in potential or electric field. That is electricity only. Electric field. Okay, that is electric work. Or charging a capacitor. That is charge moving through electric field, right? Charging a capacitor. Next up, how can conservation of mass be applied to a domestic LPG cylinder which is in use? Okay, LPG cylinder, uh, 2.13. So LPG cylinder, what is it having? Just one outlet. Okay, so it has got outlet, doesn't have an inlet. Okay, so it will be having something like this. Okay, doesn't have an inlet, just a control volume over here and outlet. Okay, so what will be the conservation of mass equation? So this is the entire equation, equal to dm cv by dt. What we don't have is this one. Inlet is not there. Inlet somebody has already filled and we have received it. Now our system has got gas inside the control volume and outlet is there. So whatever is exiting is going to be change in control volume. So whatever change in control volume is going to come out as the outlet gas. Okay, that is only that is how we are applying conservation of mass in LPG cylinder. Next is, okay, there are a lot of questions. Okay, convince yourself that in a water heater, work is converted to heat. So what is happening? Electrical energy is the work given that is being used to heat the coil, and that is how you're heating up your water. So electric work to heat. Okay, that is the answer. Now, possible to dissipate work or heat. Work dissipate means you are converting to less usable form. Like work, if you're moving something on a frictional plane, then uh, what is happening? Then some of our work, that effort that we are using to push that object is being dissipated into the atmosphere as frictional heat. Okay, so that is what we are saying about dissipation. is it can dissipate because it is a kind of a energy change that is happening, like one form of energy to another form of energy. That is how it is happening. So that is a yeah, you can say that it is dissipation only, but you cannot say that uh, work is being destroyed. That is not there, because uh, work and heat and all those things are form of energy. Energy cannot be destroyed. So it is dissipation means it is converted to another form. Okay. Now another thing is, what is the difference between energy of a system and internal energy? Energy of a system E is U plus P plus K. Okay. In that U, internal energy is microscopic, uh, way of calculating energy. The other two are bulk form of energy calculation. So energy of a system will have microscopic and bulk form of energy, but internal energy just it will calculate only the thermal, due to the temperature, the molecule vibrating at a microscopic level. Those things will be scaled in internal energy. Now, while charging a cell phone, the internal energy of the device is being increased. Comment on the validity of statement. Yes, it is increasing. Uh, yes. Why? Because first of all, when you're charging, temperature increases. That means charging means temperature increasing. So that means internal energy is increasing. Another way of looking at it is chemical energy uh, is replenished. So that means you are increasing U again. Okay, chemical energy replenished means internal energy is replenished. So yeah, while charging a cell phone, internal energy of the system is increased. What is internal energy? So you imagine this thing like a chemical reaction is about to happen. You have got two reactants. Okay, so until that is how we are. If you are having TV remote, you are putting a battery in that. Okay. So what is that internal energy? So how we are getting electricity? That internal energy is being converted to electricity. What is the internal energy in that battery? That is the chemicals inside that battery. So once the chemicals are over, that means internal energy is sort of you know dip, depleted. That means then you are not able to convert it to the work. So that internal energy was being converted to work. So when battery chemicals are over, internal energy is over. That means you cannot convert it to work. That is why you have to change that battery in remote after some time. So when we are using phone, again the same thing is happening. We are using secondary batteries. That means it can be charged again and again. So every time you are charging, you are sort of reversing some reaction that was happening inside the battery. um, it was like some A plus B was becoming C. That is how you were getting electricity. Okay. So once this whole of A and B is changed to C, then your internal energy is zero. I mean, you cannot say it's zero, but it is at very low position that you won't be having charge in your phone. Like you cannot use your phone. So when you are connecting it to some electric sources, you are reversing this C to A plus B again. So that is when you are charging it. That is when you are increasing the internal energy. Okay, so that is what is happening. Now, can internal energy be observed at the boundary of a system? No, because it's a property. Okay, property of bulk. So you cannot observe it as it at boundary. It is stored inside the system. Is it true that every substance has internal energy? Yes, unless it is at absolute zero. Okay. Then, can internal energy be observed? Okay. Uh, Comment on the statement. Internal energy of an isolated system will be constant irrespective of process happening inside it. Yes, isolated system means what? So what is the first law? Q delta Q equal to delta W plus delta U. Okay. Okay, that is the first law. So isolated system is Q is 0, W is 0. So delta U equal to 0, that means U is constant. Okay. Now next is SI unit of energy, internal energy, heat and work are kilojoule. Is this statement correct? No. Energy SI unit is joule. Kilojoule is another metrics of SI unit is joule. Okay. So kilojoule is again, if you are having 10 to the power 3 joules, then you are saying it as kilojoule, but the basic unit is joule only. And K is what? Kelvin. Kelvin is unit of temperature. For temperature. Okay. Then next is ice is dropped in the warm water and the vessel is isolated from the surroundings. With time, the ice keeps melting. As a result, the internal energy of the system will change. True or false? So, ice is melting inside a vessel that is isolated from the surrounding. Again, isolated means what? U is constant. So then, what is happening when ice is melting? When ice is melting from warm water, heat is going to ice. Okay, but this is a whole system. That system U is constant. Okay, so heat is flowing inside system. Sorry, heat, not heat. Sorry, I should not have said that. Internal energy is not flowing. Okay, I'll remove everything. Let's see. Internal energy is rearranging in a system. Internal energy is rearranging inside the system itself. Okay, but it is not changing, it is constant only. So as a result, internal energy of the system will change, that is false. Okay, 2.22. Okay. Now, 2.23, can we say that for a system that is in equilibrium, its internal energy does not change? Yes. For a system that is in equilibrium, internal energy will not change. Yes. Why? Because if chemical composition is not changing, then the chemical thermal the chemical equilibrium is attained. Then thermal equilibrium is attained, means there is no heat flow. Then work is not there, that means there is mechanical equilibrium is also there. So if it is in equilibrium, then can we say for the system that is in equilibrium, internal energy does not change? Yes, that is true. So Q equal to 0, W equal to 0, delta U equal to, this is W equal to 0 is mechanical equilibrium. Okay. Q equal to 0 is thermal equilibrium, and delta equal to 0 is chemical equilibrium. Okay, so that means U is constant. A metal bar is heated at one end and cooled at the other. The bar system is in the bar or system is in steady state. Is it true that its internal energy remains same? Yes, internal energy remains same. If steady state means again the temperature or the internal energy is rearranging. Okay. Steady state means no accumulation of heat. That's it. Steady state means no accumulation of heat. Okay, so that is true. Okay, what is happening is, so you are heating. Okay, steady state means what? Temperature is not changing with time. Temperature is sort of a measure of internal energy. So if temperature is not changing, that means internal energy is not changing. Only thing is this internal energy is sort of rearranging itself from heat, cold part of the bar to hot part of the bar. That's it. But otherwise. The heat is not getting accumulated, so that means internal energy is same or constant. Now, comment on the validity of the statement. Internal energy is a property of the substance in the system, and specific internal energy is also a property of the material of the system. Internal energy is a property of substance of the system. That's true. Okay, that is true. It depends on the mass. Okay, 2.25. Internal energy depends on mass, and specific internal energy is kind of like density. That means intrinsic property. That means it doesn't depend on the mass. Internal energy is intrinsic property, changes with material. Okay, so for steel it will be one value, for wood it will be other value. So that is how it will be. Okay, so that is about the review questions. I hope it was very helpful, this discussion. And if there are any other doubts, please feel free to write it to me. And that's about it. Thank you.